Hi, and welcome to the 6th tutorial video for this term. This tutorial has problems relating to impulse and momentum. The first problem states, the log has mass m and rests on the ground for which the coefficients of static and kinetic friction are μs and μk respectively. The winch delivers a horizontal towing force T to its cable at A, which varies as shown in the graph. Determine the speed of the log when T equals T2. Originally, the tension in the cable is 0. As a hint, we need to first determine the force needed to begin moving the log. In this problem, we're dealing with a force profile that doesn't stay constant. We also have to deal with static friction instead of the more simple kinetic friction. We already learned how to analyze pulley systems from previous tutorials, so I'll skip that part. We can see that the force exerted on the block by the string is 2 times T, which balances out with the static friction when the block is not yet accelerating. I will use this yellow dot to track the tension force as it increases with time. The force of static friction will increase to perfectly oppose this tension force, until the static friction force reaches its maximum value, which is μs times the normal contact force. Let's say that the static friction force is overcome at time t0. From a perspective of motion, this means that we can essentially ignore anything that happens before t0. Right at time t0, the block breaks free of static friction, and the friction force becomes kinetic friction, which is smaller since the coefficient of kinetic friction is smaller than the coefficient of static friction. By setting the sum of forces in the x direction equal to 0, and using the maximum static friction force, we can solve for t0, and we find that it has a value of 2.48 seconds. Now we can move on to solving for the final speed. The momentum of an object is denoted by p, and it's given by the mass times the velocity. The impulse j is the change in velocity, and the impulse provided by a known force can be found by integrating that force over the time period during which it is applied. The expression for impulse is why this problem lends itself well to impulse and momentum. Both the forces and the time over which they are applied are well known. It would be cumbersome to use energy methods since we don't know the distances over which the forces are applied. The impulse has two parts since there are two distinct time periods to consider. The first is from t0 to t1. The two terms represent the two different forces of tension and kinetic friction. We can do the same thing for the second time period. This impulse represents the change in momentum, but since the initial momentum is 0, it's simply equal to mv2. Simply solve this equation for v sub 2, and we get a velocity of 7.65 meters per second. Now for problem 2. It states, the carriage of mass 2m is free to roll along the horizontal rails and carries the two spheres, each of mass m, mounted on rods of length L and negligible mass. The shaft to which the rods are secured is mounted in the carriage and is free to rotate. If the system is released from rest with the rods in the vertical position where theta equals 0, determine the velocity vx of the carriage and the angular velocity theta dot of the rods for the instant when theta equals 180 degrees. Treat the carriage and the spheres as particles and neglect any friction. I found this online physics simulation for a cart and pendulum system, which I hope helps give you a visualization of how the system would move. The simulation also has a spring, but I set the stiffness to a really low value so that it doesn't have a significant impact. You can see that as the pendulum falls to its lowest position, the block is moving to the right. Let's see that one more time, again noting how the cart is moving in the opposite direction of the pendulum. Now with that in mind, we can get to the math. Since the cart is symmetric, we can treat the two pendulums as a single pendulum with twice the mass. As we saw from the simulation, at the bottom of the swing, the arm has an angular velocity of theta dot in the clockwise direction, and the cart is moving to the right with a velocity of v sub x. Since we have two unknowns, we're going to need at least two equations. The first will be conservation of momentum in the x direction. There are no external forces acting in the x direction, so the impulse is 0. The final momentum is 2m v sub x for the cart, and 2m times v sub x minus L theta dot for the pendulum bob. If you're confused about the velocity of the pendulum bob, it's the combination of the motion of the bob relative to the pivot point and the motion of the pivot point itself. The initial momentum is 0, since the system is released from rest. That gives us our first equation. Next, we can use the conservation of energy principle for a second equation that relates the two unknowns. There isn't any external work, but there is a change in gravitational potential energy and kinetic energy. You should all be pretty well familiar with energy methods by now, so I'm going to skip some of the details. With these two equations, we can find that v sub x is the square root of 2gl, and theta dot is 2 root 2g over l. Lastly, we have problem 3. It states, the system of three particles has the indicated particle masses, velocities, and external forces. Determine r bar dot, r bar double dot, t, h about O, and h dot about O for this three-dimensional system. I'm not sure why, but I recreated the graphic here. I think I just thought it would look nice. Anyway, this is the first time in these tutorial videos that we start to think about the standard basis of coordinate systems. The x, y, and z axes are simply directions from an origin point. Mathematically, it becomes useful to define a unit vector, that is, a vector with a length of 1, which points in the same direction as each of these axes. That's where these come in. I, j, and k are unit vectors which point in the same direction as x, y, and z respectively. The hat, or caret symbol on each letter, denotes that it is a unit vector. You should get used to this concept since it becomes more and more important for dynamics. The question asks for a lot, so let's take it one at a time. R bar is the center of mass of the system. We can find it by taking the weighted average of the positions of each particle and using the mass of each particle as its weight. Notice how I'm using the I, j, and k vectors to denote the position of each particle. After expanding the expression, we can simplify down to the answer. R bar dot is the average velocity of the system, or the velocity of the center of mass. The process for solving is pretty much the same, but now we use the velocity of each particle instead of its position. The one that is tricky is the velocity of the leftmost particle. Its velocity is first broken into the z component and the component on the xy plane. Then, the component on the xy plane is further broken into x and y components. Next is r bar double dot, which is the average acceleration of the system. This one is actually quite straightforward, since acceleration is the sum of forces divided by the mass, or Newton's second law. T is the total kinetic energy of the system, which we are already well familiar with, so that one's pretty easy. H about O is the first new concept here. It is the angular momentum of the system measured from the origin O. We can find the angular momentum of each particle by taking the cross product of r and its linear momentum. Doing this term by term for the first, second, and third particles gives us this result. The math can be pretty tedious, so it's important to find a method for cross products which you can nail every time and not make mistakes. Lastly, h dot about O is the rate of change of angular momentum, and it's given by the net moment acting on the system. The moment for each particle is given by the cross product of r and the force vector. We can write the terms for the two forces, and then simplify down to the final result. That's it for today's video. As always, you can contact me at this email address if you have any comments or questions. Thanks for watching, and I'll see you in the next video.